So this is our Gate 4.5 presentation. Um, this is for Group 22. Our project is building a 3D printer, and our teammates are Mo Griffith, Daniel Gerdes, Tyler Sheets, Aaron Torres Gonzalez, Zachary Wu, and Jeffrey Dahman. I already mentioned who our teammates were on the first slide, but here are some pictures of everyone on the team. The first one's obviously Mo, the second one's me, Daniel, the third one's Zachary, the fourth one is Tyler, the fifth one is Jeffrey, and the last one is Aaron. Our problem description for our project is that basically right now in industry 3.0 and 4.0, 3D printers and additive manufacturing is becoming a lot more popular within the industry, which means that a lot more students need to learn the skills going in before they get into the industry so they can have an advantage and also just to know what they're doing when they get to that point. And basically, 3D printers are still super expensive and very inaccessible for both high schoolers, college students, and middle school students. So the goal for our project is to make a cheaper printer that is very easy to assemble, is safe, and then can also be purchased very easily, um, and provide access to people who might not normally be able to afford a 3D printer. For our project, the scope of work and method is basically that we need an affordable, functional, safe, and simple enough 3D printer that anyone can use it. Um, Basically, we need to have some form of safety guidelines that can be put in place to also keep middle schoolers safe when it comes to actually touching or involving themselves with the printer. So that means having something around the printer that prevents them from touching the hot end, because obviously that could result in pretty bad injuries because it gets very hot, the hot ends of the 3D printers. And then also we intend to take inspiration from pre-existing printers. Obviously, there's the famous saying, "If it ain't broke, don't fix it." And so obviously a lot of these printers on the market are clearly doing things right because they've sold thousands of units of these printers. And so it's like we're taking a lot of inspiration from different models like Prusa and Creality to implement into our own, but put our own twist on it to make it cheaper and simpler.
With these design goals in mind, these are some of the compromises we made to hit our goals. The first main design decision was a cantilever design. This could save costs while not sacrificing any function, and this would simplify the build process by reducing the amount of aluminum extrusion used in our design. This would also remove a lot of steps required for assembling a second Z axis on the other side. Electrical wiring is also simplified, with all of it going down a single wire managed channel in the Z axis. The second compromise we made was a 180 by 180 by 180 build volume. This is larger than most budget printers that have a build volume of 150 millimeters squared, but still small enough to be manageable and large enough for usable parts. The other major design decision was an optional enclosure. While some printers included enclosures or had built in enclosures that allowed the printer to heat faster and print advanced engineering materials and provide additional safeties, we simply couldn't fit this into our cost, but the user could print their own enclosure brackets, add in their panels, and then that would give them a fully functional enclosure.
Here are the assumptions and constraints imposed on our design process. So the first assumption that we made was if the instructions are clear and more in depth enough, we can make the printer more complicated. And by doing this, we are going to make the instructions have a step by step process. So if we include a more complicated process or something that a middle schooler wouldn't understand, they can look at the instructions and easily understand what's going on and how they can build it. Another assumption that we made was that we were going to, for the mass-produced printer, we will include outsourced parts to bring down the cost. As of right now, our prototype is not in the realm of what the budget for the printer that we want to be as. So we will be using outsourced parts from Alibaba Express and other out-of-the-country shipping sources to bring down the cost. And the final constraint that we had for our design is we want to use the least amount of 80/20 possible to lower the cost. 80/20 is very expensive, and we wanted to use as little as possible to lower down the cost. For state of the art, we are going to make a bunch of printers on the record for middle schoolers, and some categories that we had for it are safety. So we wanted a protective case around the printing table so middle schoolers don't burn themselves and that they are safe as possible. And when we were looking at printers, we came on two options. We came on a filament printer, which has a hot nozzle, or a resin printer, which we considered safer, but we found that the resin printers were a lot more expensive and a lot harder to make than a filament printer, so we decided to go with the filament printer and have an enclosure around it. The average cost of a average printer is $250, meaning it's not accessible to middle schoolers or schools because they are on a tight budget, and we want to make it as cheap as possible at having a $125 price point for our printers.
Now moving on to design requirements. The metrics we used to measure our design requirements for our 3D printer were safety, affordability, and simplicity. Starting off with safety, we needed to make sure that the 3D printer was safe enough for middle school students to use. And to verify this, we looked at safety requirements for middle school students prior to creating our prototype. Moving on to the affordability portion. The biggest restraint for our project has been the affordability portion, but the way we've been verifying this is looking at parts on AliExpress to gauge our budget as we continue to build our 3D printer. The simplicity. Our 3D printer needs to be simple for middle school students to build. To verify this, we will have a test subjects and individuals with low technical knowledge to see if they can build the 3D printer and are able to follow along through our steps.
So for our system solution, our current prototype is based off of the Prusa Mini. We chose a design like this one because it uses minimal structural components so that we can keep our costs down. We've been implementing other more affordable components such as the hot end, which only costs $5, and it is used on a multitude of different printers, making it a very common part. We are also using a common build plate that uses cheap and basic components. Currently, we are in the process of finalizing some of the structural components and doing the electronic system. We chose to use cheap and common power supplies, microcontrollers, and screens to help keep the costs down. So right now for our results, we don't have many results because we haven't been able to get a print output out of their current prototype that we have. But as of right now, we are still a little bit high with their current prototype cost being around $350. We are currently trying to get that price down, whether that be a cheaper power supply that will be able to give us the same amount of voltage that we need. Also, we noticed in our current prototype, the filament extruder that is being used currently is pretty complicated, using expensive components like bearings and different idlers. So we are currently in the process of trying to come up with a new way that we can implement something that will give us the same results. So currently we're going to try to use what we have and see if we can get the results we are looking for with our prints, and if we can do some other design that will be able to equate to that.